All right, so I guess you guys extended the lecture today a little bit, so I decided to start early and just record myself so that you can go over this later when you have time. So I would like to start finishing up the example I presented last time, or I ended with last time, which is about finding all the points of intersections of the curves r equals 2 cosine 2 theta and r equals 1. And I have noted that this is the graph of a rose with 4 petals. It has 4 petals because here n equals 2, which is even. I need to twice that to get the number of petals. And I guess last time we did the graphing here. And yeah, and I guess we stopped at finding the points of intersection because I did what we usually do, put the two equations or the two right-hand sides of the equation equal to each other and got these 4 theta values. And these 4 theta values will correspond to these 4 polar points, right? And if we will look at the graph, so where does this POIs lie? So we have first 1 over 5 pi 1 over 1 comma pi over 6. So we got that here. The next one is 1 comma 5 pi over 6. So that's going to be this point. The other one is 1 comma 7 pi over 6, 7 pi over 6. So that would be here. That point over there. And the last point is 1 comma 11 pi over 6. So that's going to be here. All right. And you see that using that solution alone will only give us 4 points of intersection. But if you look closely at the graph, we missed some of the points of intersection, like this one, this one, this one, and this one, right? So why did we miss those? Well, this is one peculiar thing about polar curves, because remember the R value can be interpreted to be a negative number, or could be taken as a negative number, but you draw the or but you if r is negative, you draw in the opposite theta direction, right? So that means I am really missing half of the points of intersection because I only considered those theta values when r is equal to 1. There could be instances wherein r is equal to -1 and will give me a point of intersection, right? Because if r is -1, then a little adjustment can be made to the theta value, or in plotting in selecting the direction in which you will plot the point, and then that will be another point of intersection, and that is what exactly happened here. So to find the other points of intersection, we also solve this equation. The right-hand side of the rows, 2 cosine 2 theta equals -1. And we hope that this will give us the other 4 points of intersection, right? So here we'll have cosine 2 theta equals -1/2. And then we're looking for the angles 2 theta, whose cosine is -1/2. So that would be, first would be on the second quadrant. We'll have 2 pi over 3. Then another one on the third quadrant, that's 4 pi over 3. And since we're looking for 2 theta, that means we'll need to take another revolution, but that means adding 2 pi to these two guys we already found. So we'll have 8 pi over 3 and 10 pi over 3. And then we divide both sides by 2 to get our theta values. So we'll get pi over 3, and then 2 pi over 3. and then 4 pi over 3 and 5 pi over 3, right? And these angles are different from the ones we got before. And let's see what does this give us. So this gives us, or this gives us the polar points 1 comma pi over 3, or negative 1 comma pi over 3, negative 1 over 2 pi over 3, negative 1 over 4 pi over 3, and negative 1 over 5 pi over 3. And let's see where these points lie. Let me just copy paste them so that I don't need to go back here. Okay, let me put that here. Okay, so we have negative 1 comma pi over 3. So pi over 3 would be somewhere here, right? But we'll be going in the negative direction. Maybe I should draw it like this. So say this is theta equals pi over 3. But since our radial value is negative 1, we go in the opposite direction, 1 unit there. That gives us this point of intersection. And then 2 pi over 3 is somewhere here. Right, that's theta equals 2 pi over 3. But since r is negative 1, we go in the opposite direction. Unfortunately, my sketch is not that good or not that symmetric, but ideally we'll get this point. Sorry, yeah, it should be this. Opposite direction should be here. Okay, so we plot here, we get this point of intersection. And then these two guys will give us these, right? So that completes the points of intersection for our graph, right? So that's a lesson there. So that's why it's important to know how many points of intersections are we expecting. So in this case, we expect 8 by looking at the graph. There would be 8 points of intersection, which makes sense because you have a you have 4 petals for your rose, and then you have a circle, and it's easy to imagine that we will have 8 points of intersection. There would be 2 points of intersection per petal, right? So if you solve, if you use our usual solution for POIs, that is just equating the right-hand sides of the two equations defining the curve together, right? So we will only get 4 points. So that will tell us something is missing here. And sure enough, one way to remedy this is to consider the negative R value, or the negative counterpart of your R value, right? And again, the reason there is that R can be negative and the adjustment is done at the angles themselves, okay? So that gives us the rest of the points of intersection. Now let's go to finding the area. So setting up the integral for the area. Let's have this. Oops, I cannot copy it properly. Here you go. Okay, and you want to get the area of the shaded region. Okay, hold on, I forgot to shade this area here. Had my picture been more symmetric or more accurate, then the petals will be symmetric to each other. So instead of integrating or setting up integral for each of the petals, right? I could just compute the area of, say, one of these 4, just say this one, and multiply my answer by 4 because I know that roses are symmetric. So, or the petals of the rose are symmetric. So that means it suffices to get the area of 1 Or another thing, actually, it's not sufficient. I should also mention that the circle is also symmetric, making the shaded regions or these 4 subregions equal to each other, right? Again, my figure is not drawn to scale, or it doesn't even show the symmetry. But the thing is that I can just set up the integral for one of these 4 subregions and multiply that by 4 to give me the actual answer. But another thing I can take advantage of is if my plan is to multiply this by 4, I can also just take half of it, because I know this would be symmetric to the lower portion. So their areas will be equal to each other. So what I can just do is to consider or set up an integral for this area and multiply it by 8, right? And why is that advantageous for me? Because I know that this is at theta equals 0. And luckily I have the label there that this is pi over 6. I found that angle when I solved for the points of intersection. So I can simply integrate from 0 to pi over 6. And that will give me the area of this shaded region, or this region here, the red region here. And then all I need to do is to multiply it by 8 to get the area of the yellow region. All right. And that's my plan here. Take advantage of all the symmetry to make it easier, right? So the area will be 8 times the area of, again, this region here, okay? So there's a mainstay 1/2, and then I'll have an integral from 0. Remember, I'll just be integrating from the polar axis, that's theta equals 0, until pi over 6, because I did multiply, or we will multiply this by 8, right? Okay. And then to know what would be the integrand, I'll need to draw a radial line here, okay? And then try to see what is the inner and what's the outer radius, right? So let's zoom in a little bit here. And then our integration is from 0 until pi over 6. So we will travel through the region counterclockwise, right? And all throughout this region that I just scanned, right? You see that the outer radius is always, the outer radius is always the black curve, and the inner radius is always the red curve. All right, so no need to split the integral up. So that means, okay, from 0 to pi over 6, my outer radius is the black curve, and my inner radius is the red circle. So that means here I'll have outer radius squared. So I'll use the equation for the black curve. The black curve has equation 2 cosine 2 theta. 2 cosine 2 theta quantity squared, or let me use parentheses here, minus inner radius squared. The inner radius is the circle r equals 1, so I'll have just 1 squared times d theta. So that will be the area of the entire shaded region. And remember, I multiplied it by 8 because I just computed the area of the region from 0 to pi over 6. So that will just be this guy. And there would be 8 of these all through to complete the yellow region. All right, so I guess that completes example 7 here. Oh, finally, hello, Farouk or Mohammed, hello. I guess that the lecture went long today. Oh, sorry, it's Tasmia, yeah. I only saw your last name. Yeah, did the lecture went very long today? Oh, okay, yeah. I figured, yeah. I was checking the academic calendar several ways, several times a day, thinking, do we still have classes today because nobody's showing up? But okay, since you're the only person here, do you want me to discuss a certain topic or a certain example? Because my plan is to go over one example of setting up areas with polar curves in which you need to subdivide the region into several pieces because the inner and the outer radius or the radius changes. And by the way, I started recording the session earlier so that you guys can just watch it later when you have free time. Okay, yeah, that's fine. I would just like to complete the discussion of polar curves, and then you guys can watch it later. I will also share the video from my other class because that starts at 12. So that means that we were not too affected by by the over the lecture overtime. So I was able to discuss more problems there. So you can also watch it when preparing for the finals. So let's see. What was my other example? Oh, there we go. Yeah, probably this would be my last example for worksheet 22. So for this example, we want to set up the integral that will give us the area of the region inside both r equals 3 minus 3 cosine theta and r equals 3 minus 3 sine theta. Okay, so first we can identify what the graphs of this equations. So we'll start with r equals 3 minus 3 cosine theta. So this is of the form a minus b cosine theta. So it's a limmason, right? And then a over b is equal to 3 over 3, which is 1. So here we have a cardioid or a heart-shaped limmason, right? And we know what to expect here. We have a cosine, so that means that the graph that the graph will be predominantly either on the positive or the negative x-axis because it has a cosine. And since its coefficient is -3, so that means it would be predominantly in the negative x-axis. So it's a heart-shaped graph, which is predominantly on the x-axis. So you should expect a graph like this, right? So even without the points, I know what to expect. So this is what I expect out of this equation, right? And to make my graph more detailed, I'll put some points. So I'll compute the values or some points on the graph by evaluating r for the quadrantal angles. So if theta is 0, pi over 2, pi, 3 pi over 2, and 2 pi. If r is 0, I'll get r equals 0, cosine is 1, so we'll get 0. At pi over 2, we get 3. At pi, cosine is -1, so we'll get 6. 3 pi over 2 cosine is 0, so I'll get a 3. And at 2 pi, we'll be back at 0. Okay. So maybe I'll put that here a little bit. Okay. Oops. Okay. Now let's try the other one. It's r equals 3 minus, or let me use a different color here. It's r equals 3 minus 3 sine theta. Okay. Now here again, it's a limmason because it's of the form a minus b sine theta, another limmason. And then to know exactly what type of limmason we have, let's look at the ratio a over b. So this would be 3 over 3, which is equal to 1. So again, we have a cardioid. But this is a bit different from the cardioid we have for the first equation because now we have a sine. And since we have a sine here, the cardioid will be predominantly either on the positive or the negative y-axis, right? And then since it has a coefficient -3, that means it is predominantly in the negative y-axis. So that means our cardioid will look like this, something like that. All right. Now again, to have a better sketch of the graph. Let's have some data, some points on the cardioid. So that is, we just evaluate the quadrantal angles. Evaluate the R values at the quadrantal angles. So when R is 0, we get 3. When theta is pi over 2, we get 0. At pi, we get sine is 0, so we'll get a 3. 3 pi over 2, sine is -1, so we'll get a 6. And at 2 pi, we'll be back at 3. Okay, so this would be our points. Then let's sketch them here. Then it looks like I need 2 radial values, 3 and 6. So let me draw some guide circles here. So this is, say, R equals 3. And then let's draw a bigger one. And say this is R equals 6. Okay. Now let's start plotting the first cardioid. When theta is 0, R is 0, so we'll be here. When theta is pi over 2, so we'll be here. And we have 3 units, so I'll have the point there. And then at pi, we'll be here. The radius is 6, so I'll have a point here. And then at 3 pi over 2, we'll have 3. And then at 2 pi, we'll be back at 0. So that means the graph will look like this. As we expected, right? Because we said that here we have a cardioid that primarily lies on the negative x-axis. Now for the red cardioid, okay, so when theta is 0, R is 3, so I'll plot that here. When theta is pi over 2, R is 0, so we'll have a point at the pole. Oops. When theta is pi, we'll be at 3, so we'll be there. When theta is 3 pi over 2, we'll be here. R is 6, so I'll draw that here. And then at 2 pi, we'll be back at 3. So the graph will look like this. It should be a more rounded graph. So, okay. Roughly, this is how our graphs look like. Let me erase the guide circles just to make it clearer. Okay. And we want to get the area of the region that is inside both cardioids. So they should be inside both cardioids. So that includes this. That's my problem when I am sketching it on a large scale. Okay, there we go. That little area there. And maybe highlighting it is not a good choice, but let me just, okay, there we go. So this is inside both cardioids, as well as this region. Okay, so that's our shaded region. They are inside both of the cardioids, right? Now, how do we set up the area? Well, there are 2 parts to this. I can consider this to be the first part, and this guy to be the second part, okay? Now let's zoom in into the little part first, okay? So let's consider this region first. Set up the integral for that, because obviously this will require a different integral, okay? Now let's look at this. So again, I want to integrate from here okay, at the start of the region until here. Until when the region will end, right? So this would be my starting and the ending theta values. So let's try to draw a line there and see what happens, okay? So we start here, and then let's scan the region. If we will scan the region, okay, so it seems that here, as I go here, the red curve is not involved for the region, because here, this red line, or the radius, will start at the pole and will end at the black curve, all right? But if I go a little bit closer to the end theta value, say at this point, now it still starts at the pole, but ends at the red curve, all right? So that means there are two different behaviors here. Sometimes the radius will start from the pole and end with the black curve. And there are some times when the radius will stop at the red curve starting from the pole, right? So that means we need to split the integral up into two pieces, and we need to split it up at the point of intersection there, because at this POI, the behavior of the radius changes, right? Before the point of intersection, we are only dealing with the black curve. After the point of intersection, we are only dealing with the red curve, all right? But one beautiful thing about these two curves is that even in this not so nicely scaled sketch of the graph, you see that this portion, let me use a color here, this blue portion, wherein I only use the black curve, this has an area equal to this guy. Let me use a different shade of blue. Okay. This happened because I have a very similar equation for the cardioids. So that means the lighter blue and the darker blue sides have equal areas thanks to the symmetry of the two cardioids. All right. So that means I can just set up an integral for one of those two pieces and then multiply the answer by 2. Okay. But if you're not sure that they are symmetric, then you need to set up two integrals, right? One before the point of intersection, and another one after the point of intersection, because you have different radii over there, right? Okay, now let's start there. So I'll consider, I'll just multiply my answer by 2. Okay, so the area, okay. So here I'll use the area for the light blue one, right? And then multiply it by 2. And then what are the theta values? Note here that I am integrating, or what I'll do here is in the lighter blue side, okay, the radius is determined by the black curve. So I look at the black curve, right? And the black curve here hits the pole at theta equals 0. So that's how I know that the lower bound is theta equals 0. All right, because I will start at the pole until I reach the POI. But to get that POI, I need to solve the equation a little bit, right? So the POIs, which I should have done earlier, but it doesn't matter. Let's do it now. Solve for the POIs. So we'll have 3 minus 3 cosine theta equals 3 minus 3 sine theta. Okay. I can subtract 3 from both sides. So I'll have negative 3 cosine theta equals negative 3 sine theta. Divide both sides by negative 3. So we have cosine theta equals sine theta. And what are the angles when sine theta equals cosine theta? So that would be just theta equals pi over 4 on the first quadrant. And the other one is on the third quadrant, which is 5 pi over 4, right? When they are both negative. And true enough, so here we found out that this is theta equals pi over 4. And this one is theta equals 5 pi over 4. Okay? So now I know that the first integral will be from 0 to pi over 4. And again, as we have noted, the radius here is determined by the black curve, which is 3 minus 3 cosine theta. 3 minus 3 cosine theta quantity squared. There's no inner radius because the radius always starts with the pole, theta equals 0. And so that would be our first part. And again, I simply multiplied it by 2 because I know that, okay, here, again, zooming in, the light blue portion, yeah, has equal area to the dark blue portion. Oh, hi, Merle. No worries. Tasmia mentioned it earlier. Yeah, Herson, yeah, it's fine. I just recorded, I started recording myself and finished example 7, then I went to example 8. And then I'll just share with you guys the recording for my other lab class, which will start in 15 minutes, so that you can watch it if you want to see more examples. So yeah. Okay, so yeah, it's fine. All right, let me just finish this. Okay. And fortunately, Morel, I need to leave in 5 minutes because my other lab class starts right after this class. But if you have questions regarding that, I hope it's not yet due. I can help you tomorrow during office hours at the CASA tutorial centers.
It is due today. It's
Oh,
6, but will you be okay if I DM'd it to you?
yeah, sure. You can send it to me, and then I'll try to answer as soon as I can. All right.
Okay, thank you.
On Herson's question, yeah, we are just starting to grade homework 5. We prioritized grading FRQ for test number 4 last week. Our deadline to finish grading it is on Thursday. So hopefully by Friday or over the weekend, you will see your grade for it. Okay. Okay, now let's continue because we have another portion here for the area that we haven't counted yet. We'll have this. Unfortunately, my sketch is not very well scaled, so you will not see the symmetry between these two guys. So let me just doctor the picture a little bit, just to convince you a little bit that this should be symmetric. Because I think it should be symmetric. A quick test will tell you that this is symmetric. But again, if you're not sure if the graphs are symmetric, then you have to set up the integrals separately. But here, I'm sure it's symmetric, so I can take advantage of the symmetry. Now, what I know here is that, okay, I'll be integrating supposedly from here. That's the first time when the, oops, let me do that again. This would be the first time when the red curve hits the pole. And let's see, when does the red curve first hit the pole? The red curve first hit the pole at pi over 2. And sure enough, we start here. That's the start of my second shaded region. And then let's play with this radial segment here and see, okay, so from pi over 2, I increase it a little bit, and you see that the radius always starts at the pole and ends at the red curve, right? So no problem. Same thing goes here. Still, I'm hitting the red curve, okay? Okay. And then now I am at the point of intersection. which occurs when theta equals 5 pi over 4. But right after this, the radius suddenly became determined by the black curve rather than the red one. Oops, come on. Okay. So this would be my radius from the pole until the black curve. And that's quite different from what we encountered before the point of intersection, wherein the radius is until the red curve, right? Red curve, red curve, red curve, and then we hit the POI. Right after the POI, the radius is determined by the black curve, all right? So that means I need to split the integral up into two pieces, integrate from pi over 2 until 5 pi over 4 using the red curve, and then from 5 pi over 4 until 2 pi, integrate using the black curve. So if you're not sure about the symmetry, then you need to use two integrals, pi over 2 to 5 pi over 4, another one from 5 pi over 4 until 2 pi. But since I'm sure that they are symmetric because the two equations are very similar to each other, they are cardioids, exactly the same cardioids except for the trig function. So that's how I know that they should be symmetric, or this region should be symmetric. So I can just set up the integral for the light green portion here and just multiply it by 2. Because this region has the same area as the one with the dark green side. And I'll just multiply the answer by 2. So here I'll use the light green region. So 2 times the mainstay 1/2 integral from pi over 2 until the point of the theta value at the POI, 5 pi over 4, and then radius squared. And again, from pi over 2 to 5 pi over 4, the radius is determined by the red curve. And then the equation of the red curve is 3 minus 3 sine theta quantity squared d theta. All right, and that completes the area. Okay. I guess that's all the time I have for today. Unfortunately, we're not able to answer some problems about parametric curves. I hope to cover examples of that in my other lab class. So I'll just share with you guys the recording of that session. And hopefully we'll be able to cover more examples than what I covered today. And also, I guess this is the last day of classes, so yeah, I guess this would be farewell for us for now. Thank you for the nice semester. I really enjoyed the class. You've been interactive. Yeah, unfortunately, Morel, I'll be graduating this this spring, so this would be my last year here at UH. So yeah. But nevertheless, I hope you guys succeed in your courses. And yeah, if you have some questions and you think I can still help you, I'll try. You can still send me some emails if you have some questions. I'll be happy to help you. I might be in a different time zone then, but I'll try to answer you as soon as I can. Also, you can send me an email via my my up.edu.ph email. I don't know if you have it, but visit my website. I'll continue to post the materials for my classes there. I don't know what classes I'll be teaching next semester back in my university in the Philippines, but yeah, if you have questions, just let me know, and perhaps we can still keep in touch, and then yeah, I can help you as soon as I can, though I'll be in a different time zone. Right? Oh, thank you, Herson. Thank you, Morel. All right. So I guess that's it for now, guys. But I'll still be available for CASA tutorials until the end of the official end of the session, which I guess is on May 13th. So you can still catch me in CASA from on Tuesdays and Thursdays from 6 to 7 p.m. But you can also send me occasional chats via Teams until I am still a student here in the UH. I don't know. I doubt if I'll have access to this Teams account after I graduate, but use my other email if you want to contact me. All right, guys. So thank you, guys. Good luck, and see you around. Bye.